This is the brief on geometric couplings and high-order tensor identities. So, what are we talking about? We're diving into a complex math identity that describes how two twisting vector fields interact. This relationship is called geometric coupling, and it's absolutely crucial for modeling things like fluid dynamics and electromagnetism. All right, so let's break this down into the three key takeaways you really need to get. First up, the result. The output components of this identity, we call them covariant components, are instantly determined by how the two input fields are oriented. As those inputs twist, the output size and direction are constantly changing. This proves the identity isn't static, it's an active, geometric-dependent coupling, showing how the fields dynamically influence each other's rotation. Okay, second, to really use this, we've got to move beyond simple grids. To figure out the curl of a vector in any coordinate system, which is vital for physics and curved space, you have to transform it from its basic Cartesian form. And for that, you need two special tools, the metric tensor and the permutation tensor. They help define distances and relationships in those non-standard spaces. And finally, visualization. These complex tensor identities can feel abstract, but they have to translate to reality. So creating a dynamic geometric picture of this identity is a crucial check. When you map it out and see the output components constantly shifting, it confirms the theory. This identity is describing a truly active and responsive physical system. So understanding this geometric coupling and the role of coordinate systems is absolutely key to defining and visualizing these complex tensor identities, no matter the basis.